don't take you take 0.5 as the position, or you take like the total displacement from the first 0.5 to the second 0.5?
Yeah. So this is particle kinematics. Number 5, you said? Okay. And let me just draw what's going on here. So a ball's thrown into the air from a starting height of 0.5 meters. That's half a meter. Okay, so it's thrown from a height of half a meter. And it reaches a high point of 5 meters above the ground and then comes back down. I guess that's not drawn to scale. And it asks for a few things. Maybe we should, I don't know, maybe we'll go through this, see if anyone else is curious about this. But the question is, what's the velocity of the ball at the instant that it's at 0.5 meters high on the way back down? And so you're not, the question is like, so do you have to figure out the whole distance that it travels, or do you just use the position again at 0.5? And when we're talking about positions, we're just talking about the coordinates of the object. And so it starts out with a position of, well, not coordinates because we're in 1D, but we're just talking about the sort of the position label at each instant. So you can think of it as like 1D coordinates, you know? And so it starts out with a position of 0.5, it goes up to a position of 5, and then it comes back to a position of 0.5 again. That's right. Yep. And did anyone else have questions about this one, or did this one? Yeah. Okay. Yeah. Maybe I'll just go through this. But the interesting thing is, so when you put this into the equation and you specify like, okay, now I want to find the velocity when the height is 0.5 meters, you're like, well, how does it know that I'm talking about when the position is 0.5 meters on the way down as opposed to on the way up? And the answer is there's always going to be some kind of square root in there that's going to make it plus or minus. Okay, so the velocity is going to be plus or minus depending on which direction it's moving. And the magnitude of the velocity is always going to be the same. So if you have free fall, so if air resistance is negligible, and that's a big if, but we're always assuming that in these calculations. Whatever, let's say that we'll calculate it, but whatever the velocity was at the instant it was released in a positive direction up, when it comes back down, it's going to have the same magnitude, the same speed, just in the opposite direction. So if it takes off at 10 meters per second, it's going to be 10 meters per second on the way back down too, which is why people tell you not to shoot guns into the air on New Year's Eve, you know? Because so bullets have, you know, there's a terminal velocity, they're going really fast, so there's a lot of air resistance. But if you neglect air resistance, the bullet comes right back down at the exact same speed that it was shot, you know? So don't get in front of it. Don't try to catch it.
Why wouldn't we use gravity 9.81 if it's coming back down? If you throw it up, then it hits the stopping point and then falls like free fall gravity, right? So
yeah, the whole thing is in free fall.
But
that's
you
right.
said it would be at the same speed as if it was thrown up, but it would actually be 9.81.
Acceleration is is 9.81 down. Velocity
Oh, okay.
changes the whole time. So remember so any kind of free fall graph, position versus time graph, looks like some kind of parabola. Okay. And so a parabola, the slope is changing the whole way. That slope is the velocity, and it's the concavity that's the acceleration. That's constant. Okay, so let's go through this. So first, we want to know what's the starting velocity. What's the initial velocity? What? Yep, that's what we're trying to calculate. And second, we want to know the velocity when it returns to a height of 0.5 meters. And then C, what's the velocity the instant before it hits the ground? See how motivated I am after we finish A and B. What's the velocity just before it hits the ground? Okay, so to find the initial velocity, we have these equations. Position as a function of time is equal to the position at time 0 plus the velocity at time 0 times the time plus 1/2 a time squared. And then we also have the function v as a function of time is equal to v sub 0 plus at. And then we also have a combination of these two that doesn't use time explicitly that I think you had to solve for in your homework. Before we can do this, so any kind of problem where we're going from a description in the real world to equations, we have to choose a zero position and a positive direction. And I mentioned before, I pretty much in these problems always just choose my 0 to be the lowest point in the problem. So that's the ground in this case, and my positive direction up. And in these kind of problems, there are only 6 or 7 variables that can come up. So let's see, there's the time, the instant that you're talking about, how much time's elapsed since the 0 time at the instant you care about, the acceleration, the position at time equals 0, the position at the time you care about, the velocity at time equals 0, the velocity at the time you care about, and I think that's it. 1, 2, 3, 4, 5, 6. So we can just go through and figure out like which ones of these we know, figure out what we're trying to find. So of these, for part A, what are we trying to find? That's right. We're trying to find V0. And so we need an equation that has V0 in it, and everything else in it is known, because in a single equation, you can only solve for one variable. Okay? So let's see. We don't know the time. So I think actually the one we need is the combination of these two. Or you could combine them yourself, but these two combine to give you one that says, the form I put it in was 2a times the quantity p minus p0 is equal to v squared minus v0 squared. And this is the one, we're looking for this. And if you're looking for v0, obviously the equation has to have v0. and everything else is known. We know the acceleration because it's free fall, the position at our chosen time, initial position. What's the position at our what's the velocity at our chosen time? At the highest point? 0. So we can use this one. Is acceleration, what's the sign of the acceleration? Negative, because our positive is up and acceleration is always down. So we have 2 times negative 9.81. I'll keep the units in for now. Times the quantity. P at the chosen instant is 5 meters. The position at time equals 0 is 0.5 meters. That's equal to 0 squared minus v0 squared, which we're trying to find. So this is negative, 2 times negative 9.81, negative 19.62 meters per second squared times 4.5 meters is equal to negative v0 squared. Can someone multiply 4.5 and 19.62? These negatives cancel. Okay, so v0 squared is positive 88.29. And the units, you can just multiply all these like algebraic variables. So you have meters squared over seconds squared. And you can see that when we take the square root, the units are going to come out like they should. And that always works in every scientific equation. So if you have the time and energy to keep your units in the calculation, it's a way to sort of catch yourself on mistakes if the units don't come out. A lot of times that's not the only mistake in the problem. You did some step wrong, and this will help you find it. But take the square root of both sides, and you get v0 is equal to plus or minus, what's the square root of 88.29? 9.396. Square root of meters squared per second squared is meters per second. Okay, so on the way up, the velocity is one of these two. At the instant it's released at time equals 0, does it have a positive or negative velocity? Positive, it's moving in the positive direction, so the answer is this. Any questions about that? Okay, so now for part B, now we want to know how fast it's going when it gets back to a height of 0.5 meters. So we have time, acceleration, p0, p, v0, v. So this time, I mean, we might as well choose the same time equals 0 point. We know a bunch of stuff there. What's going to be our chosen time at the end of this interval that we're looking at? Or what, like, how would we don't know the amount of time, the elapsed time, but we know what's happening at that instant. What's happening at that instant? It's not stopping, it's getting back to, because this is part B now. It was at 0 for part A. Now our time t represents the instant that the ball comes back to this height. Okay. So the time is going to be whatever it takes to get back to here. The position at that time is going to be 0.5. And we're trying to calculate the velocity at that point. And we already, because of what I just said before we did part A, we already know what the answer is going to be. It should be negative 9 point whatever. Well, it was positive 9.396 on the way up. But now it's going to turn around, stop at the top, start speeding up, and it's going to speed up exactly to speed of 9.396, but now going in the negative direction. Okay, so now we're looking for this one. Okay, so is there an equation that will let us solve for this? And I think it's the same equation that'll work here. So we'll use 2a times the quantity p minus p0 is equal to v squared minus v0 squared. So we have 2 times negative 9.81 times the quantity. At our final time, our chosen time, the height is 0.5. What's the height at time 0? Well, we chose, I mean, you could do it that way, but we chose that it started at 0.5. So our time equals 0 is when it's thrown. It's thrown from the same position that it stops at our final time. And so P0 and P are both the same thing. They're both positive 0.5. Okay. So you could set up a number line, and any point on the number line, wherever the ball is at that point, that gives you the position. It doesn't matter where it's gone before that. We're just looking for labels that represent the location of that object. Okay, so we have 0.5 minus 0.5 is equal to v squared minus, and our v0 squared was 9.316 squared. Well, this side all goes away because the height's the same. Round off error. Just kidding, that's not really round off error. If you just write there. Yeah. 9.396. Okay, so the whole left side goes away, and what you're left with is something that says v squared is equal to 9.396 squared, or in other words, v is equal to plus or minus 9.396. At this instant, it's on the way down in the negative direction, and so the answer is this. And you see really clearly from this equation why it's the case that if something's in free fall, when it passes a point on the way up, that has to be the same speed as when it passes that same point on the way down. No matter what that point is, there has to be a symmetry to it. And it's because this whole side goes away when those two positions are the same. And then you just start making an equality between the two speeds. Also, if you want to understand it mathematically, if you graph the position versus time of any free fall, it's always, now we don't know where the time is, where time equals 0 is, but it's always going to be a parabola. And a parabola always has symmetry around, like its highest point. So if you choose any height, any position in the object's path, the velocity here is equal and opposite to the velocity here at the same point. Yes? Yeah. So every mathematical analysis that we do ignores air resistance. Yeah. But if you do take air resistance, like if you graph position versus time, the vertical position versus time of a baseball that's like a home run ball hit in the, hit by a professional player or whatever, it wouldn't exactly be a parabola because the air resistance would mess that up. Any other questions about that one? Okay. What's the velocity the instant before the ball hits the ground? Well, let's still choose our time equals 0 to be when it's released. Our chosen time is going to be the instant right before it hits the ground. It can't be once it hits the ground because at that point it's not in free fall anymore and these equations don't apply. So this is just before it hits the ground. And the variables we have are t, a, p0, p, v0, and v. All right, well, let's try to estimate, like, what do we expect to happen? Do we expect the velocity right before it hits the ground to be positive or negative? Negative, it's on the way down. And do we expect the speed, the magnitude of the velocity, to be bigger or smaller than 9.396? Bigger, that's right, because it has a negative velocity and a negative acceleration, and that means that it's speeding up, okay? And there's no air resistance, so there's no terminal velocity or anything like that. According to this, it would keep speeding up. So this is classical physics. This says that if you drop this object from, if you kept going higher and kept dropping it, like that speed would keep getting faster. You'd get to the speed of light, lift it up higher, it would go faster than the speed of light. We know that can't happen, but this says, according to the math we're using, it's just going to fall faster and faster and faster until something gets in its way. Okay. Okay, so what's the variable we're looking for? Velocity, that's right. And I think we're going to have to use the same equation again because we haven't ever been given anything about the time. So we're going to use 2a times the quantity p minus p0 is equal to v squared minus v0 squared. So 2 times negative 9.81. What's the position at our chosen time? That's right. And at p0? 0.5, yep. No, for the final velocity. Oh, I see. Okay, so so if we specified like a radius of the ball, like that's a good thought. If we specified a radius for the ball, we would have to do this for when the ball was, the center of mass of the ball was like a couple of centimeters off the ground or whatever. We're treating this like a particle, so we're treating this ball like it has no length dimensions. And so to us, the instant before it hits the ground is a position of 0.000, infinitely many zeros with a 1 at the end, and we'll just call it 0. Okay, so we're trying to find this V. V0 is 9.396. And so we have positive 9.81 on the left side is equal to V squared plus, nope, minus 88 point, what did we get before? 88.29. And so add that to both sides, and you get v squared is equal to 98. Yeah. So what, 98.10? Okay, and then v is the square root of this. So plus or minus, what's the square root of 98.1? 9.94. 9.904 meters per second. And if you didn't remember that the units for velocity are going to be length per time, meters per second in SI units, then you'd have to carry your units through the whole calculation, and it would tell you what the units are. Is it positive or negative? Negative. We knew that before we started. And you see that the speed is what we expect. Not too much bigger than it was for parts A and B, but a little bit. Because it's only fallen an extra 1.5 feet or so. Any questions about that one? Any other homework questions you'd like to see? All right, well, I'm going to do one more example problem. Okay, so let's say that there's this crazy out of control elevator that's moving up with a speed of 20 meters per second. That's like 45 miles an hour. And the terrified passenger inside accidentally, out of fear, drops his pet ferret. Okay. So if the passenger drops the ferret at 20 meters above the bottom of the elevator shaft, what's the greatest height above the bottom of the elevator shaft that the ferret reaches? Okay, so first let's make sense out of what's happening here. So I think for a lot of people, your intuition before you start analyzing this mathematically is, well, this guy drops the ferret just falls down to the floor of the elevator, and so the highest point the ferret ever reaches is 20 meters, right? Because it's dropped But that's not what happens. And why is it that the ferret, so the ferret will actually, even though it's being dropped from that height, it's actually, to an observer on the ground, it's going to go quite a bit higher up into the air before it starts falling back down to the ground. So why is that? That's right. That's right. So when something is dropped, its initial velocity at the point that it's released is the velocity of whatever it's dropped from. In this case, it's an elevator that's going 45 miles an hour. So the path of the ferret, if you ignore the fact that the elevator's here and all that kind of stuff, the path of the ferret is going to go way up into the air because 45 miles an hour is fast, and then it's going to turn around and come back down. The floor of the elevator might interrupt that flight before it turns around. We'll find out about that. We'll just assume that the guy's tall, the elevator's tall enough that he'll get to the highest point. And to this man, by the way, it'll look like the ferret just falls right down to the floor of the elevator. But to somebody watching it, it's going to launch way up into the air and then fall back down. Okay, so let's calculate this. So our zero position, I'm going to choose the bottom of the elevator shaft. I'm going to choose the positive direction up again. The time equals 0. I'm going to choose when the ferret's dropped. The chosen time is going to be when the ferret reaches its highest point. And now we have to think about what we know out of time, that final time, acceleration, initial position, position at chosen time, initial velocity, and velocity at chosen time. Okay, what are we trying to calculate? Well, yeah, and not really distance. We're just trying to calculate the position at the highest point. So the position at that chosen time, so this one, and of those three equations, which one has the position at the chosen time and everything else in the equation is known? And I think since we're not given a time again, the one to use is the same one, the only one we've used so far this class. The one that says 2a times the quantity p minus p0 is equal to v squared minus v0 squared. So 2 times negative 9.81 times the quantity. We're trying to find this final position. We know the initial position is 20 meters. Do we know the final velocity? We do, because we're looking for the highest point in the ferret's flight. And so 0 squared minus the initial velocity was 20. And so we have negative 19.62 times p plus 392.4 is equal to 400, negative 400. And so negative 19.62 times p is equal to 792.4 negative. negatives will cancel each other. And so the final position, what's 792.4 divided by 19.62? 40.39. Okay, that's fine. Meters. Okay, so that's how high the ferret will be if it doesn't hit the floor of the elevator before that time. It probably is going to hit the floor of the elevator before that time. We could calculate that too. Let's think about that. But so why does this give us the wrong answers if it does hit the ground of the elevator before this happens? Yeah, I mean, so just remember that these equations only hold until this object makes first contact with something else. These only represent free fall. So once it hits the floor of the elevator, then these equations don't. I mean, there might be equations that work to tell us what it's going to do, but we need to know, how bouncy ferrets are and, that kind of stuff. So this set of equations stops working as soon as it hits. Okay, so how far do you think, I guess, how far above the floor of the elevator is the ferret dropped from? 0.75 meters. That's like exactly the most common ferret dropping height. And let's say that the elevator continues to move up at 20 meters per second. So does it hit the ground before that point? Or not the ground, but the floor of the elevator? Okay, so now we're going to track the floor of the elevator. And what we're going to do is figure out so we know the maximum height that the ferret gets to if there's no floor of the elevator. Okay. We're going to figure out if the floor of the elevator is higher than 40.39 at that instant. If it is, then that means at some point there was contact between those two, because they can't cross through each other. Okay.
So this height is always hypothetical.
What?
Like this height, this position is hypothetical, assuming that
that's assuming that, right, that the floor disappeared or whatever. Yep. So now we're going to see if the floor and the ferret cross paths at any time during that flight. If they do, then at some point the floor would have stopped this free fall. Okay. Does everyone understand the idea here? Anybody have any questions to clarify what we're doing? Okay, so what we're going to assume is that if the elevator is moving with a constant velocity, of 20 meters per second up, then what's the acceleration of the floor of the elevator? Zero. That's right. So constant velocity means the exact same thing as zero acceleration, because acceleration is how quickly velocity is changing. So let's start thinking through this. The variables that we're dealing with, well, you know, zero acceleration is still constant acceleration, so we can still use these equations. So there's a time, an acceleration, a p0, a p, a v0, and a v. And let's think about what we know of these. So what we're trying to find, I guess, if this is going to be when the ferret reaches its highest point, that highest point was 40 point something. Where is it? 40.39. We're trying to find the position at that instant. We're trying to find the height of the floor of the elevator at that instant. What's the height of the floor of the elevator at time equals 0? The height of the ferret was 20 meters. The floor is 0.75 meters below that. So this is 19.25 meters.
I have one question. How come the meter is like 0.75?
We just specified that. But that was just like a, you know, a rough guesstimate of how high your arm would be. But this is just using the fact that, like, we specified that the ferret has dropped from a height of 0.75 meters. So there's a 0.75 meter distance between where it's dropped from and the floor. So when it's dropped from 20 meters, the floor of the elevator is 19.25 meters high. The acceleration is 0. V0, what's that? The velocity at time equals 0. 20, that's right. And we are going to assume that this is a trick that'll be helpful if you remember to do it. It's not totally urgent, but it can mess up some of the equations. It won't give you wrong answers. It'll just make you think you can use equations that aren't going to work and stuff. If we assumed that the final velocity was 20 meters per second, that is true, but we're going to pretend like we don't know it. Okay? So really, we do know this. But we're going to treat it like we don't. Okay, so is there an equation that works? So here are our choices. We have one that says V is equal to V0 plus AT. We have one that says P is equal to P0 plus V0T plus 1/2 AT squared. And we have one that says 2A times the quantity P minus P0 is equal to V squared minus V0 squared. Do any of those work to let us solve for P? Well, we know the first one doesn't work because it doesn't have P in it. The second one doesn't work because we don't know time. And the third one doesn't work because we don't know V. Okay? And this actually is a perfect example of why we want to pretend that we don't know V. Because if we said that we knew this was 20, we would think we could use this equation. We'd go to use it, it would degenerate, wouldn't be able to, it wouldn't give us anything useful and we would have just wasted a few seconds. It's not a big deal, but if we assume we don't know this, then we recognize right away that this equation won't work either. Okay. And if you try it, you'll just see it doesn't work. Okay, well, so is there another strategy? Yes, that's right. So what we want to do, since none of these work right away, is we're going to find t first. So to find t, we just have to go back to the motion of the ferret, figure out the time that it takes to get to its highest point, and then that's the time we'll use here. So none of these work. We'll find t first using the ferret's flight. Okay, so go back to the ferret. Temporarily. And the variables, possible variables are t, a, p0, p, v0, and v. We're trying to calculate t. And we know that this represents when the ferret reaches its highest point. We know acceleration, because it's free fall. P0 we know is 20 meters. Final position we know is 40.39, was it? Do we know the initial velocity? Yep. Do we know the final velocity? We do, because it's at the highest point. And so this is 0. And so we have two options for equations. One, we'd have to use a quadratic. The two options are v is equal to v0 plus at. The other one is p is equal to p0 plus v0t plus 1/2 at squared. Those both work, so might as well use the simpler of those two, use the linear one. So the final velocity 0 is equal to 20 plus negative 9.81 t. And so t is equal to 20 divided by 9.81. What do you get for that? 2.02 seconds. Any questions about that? So now we're going back to the floor of the elevator. Ooh, time's up. Floor of elevator. So now what equation works now that we know t final? So now we can use this position equation. So P is equal to P0 plus V0 T plus 1/2 a p squared. So position is equal to the starting position of the floor of the elevator, 19.25, plus 20 times the elapsed time, 2.02. The acceleration of the floor of the elevator is 0, so this term goes away. And so what do you get for P? $60.05. 60.05 is greater than 40.39. So the ferret hits the floor before it reaches its highest point. Anybody have any questions about that? That's really long. When I thought of doing that, I hadn't thought about it hitting the floor. So you could just do this in a really, really tall elevator standing on a ladder, and then you don't have to worry about it. That's probably the way to go.